Hello students, welcome to the EN 401 lecture on superposition and deflection. Here's the roadmap for this lecture. We're going to talk about superposition. We'll also get into applied loads at different points on a beam. We'll talk about superposition and how it applies to shear diagrams, moment diagrams. Then we're going to go into deflection. And then we're going to look at the NDS, which is the National Design Specification. And then we'll look at superposition of deflection. All right, so what is superposition? So we grabbed the definition off of Wikipedia here at the top. Superposition essentially is the principle that states for all linear systems, the net response caused by two or more stimuli is a sum of the responses that would have been caused by each stimulus individually. All right, what does that mean? We'll break that down using this picture at the bottom here in a minute. All right, big picture here though. In the case of beams, the linear system that we're talking about in our definition is the beam, right? A beam is a linear system, right? We have an object that takes up a length along the x-axis, so we have this linear system. We'll call that the beam. Our stimuli that we're talking about in this definition are our applied forces and moments, right? So if we have multiple applied forces, right, we can sort of add those up and add their reactions up to meet the definition of superposition. And then the last point here, if forces and moments and deflections are all located at the same point on our beam along our linear system, then we can add those together. So let's kind of go through and see what that looks like. So we got this simply supported beam here, pin on the left, roller on the right, and we are going to add a 10-pound load. We're just going to say that load's right in the middle. So we know that that 10-pound load is going to give us reactions of 5 pounds on either side, right? Half the load goes to the pin, half goes to the roller. Well, what happens if we add another 10-pound load? Is that going to give us an additional 5-pound reaction force at each side, right? So we wouldn't say that essentially this is two 10-pound loads with two 5-pound reactions. We could say that this is a 20-pound load with 10-pound reactions at the left or the right. So that's sort of superposition in a nutshell. We've got a bunch of, on beams, we got a bunch of different loads, and the net results of those loads and the reactions can sort of be added together so long as they're located at the same point on the beam, right, the same point in our linear system. So those are pretty easy examples, so we're going to look at something a little bit more complicated next. So what if we have applied loads at different points, right? From our previous slide, we saw that to add things up using superposition, things had to be at the same location, right? But we can end up in scenarios where the loads aren't always applied at the same place, but in our linear system of our beam, our reactions are still at the same place. So we'll just kind of see how that looks. All right, so we're going to start off with this with a 15-pound load. And we're going to say that that 15-pound load is positioned so that 10 pounds of it goes to our roller on the right, and 5 pounds goes to our pin on the left. All right, now we're going to add a 10-pound load. We're using an orange arrow here to delineate between the 15-pound load and the reactions for the 15-pound load. So we had our 10-pound load, and we look at how that 10-pound load causes reactions on our beam, and we're going to say it's located so that we get 8 pounds going to the left and 2 pounds going to the right. All right, so since our reactions are at the same place, we can use superposition to add those up, right? So 8 and 5 is 13, and 10 and 2 is 12. Right, so we've got our reactions there, which was just the sum of the reactions caused by each individual force, right? Superposition. One thing that we can't do in this scenario, though, is we can't say, oh, well, 10 pounds plus 15 pounds is 25 pounds. We'll just draw that where the 15-pound load is. We can't do that. That's not superposition, right? But we can superimpose our reactions because they're at the same location, whereas our two applied loads, they're at different locations, so we can't add those up. So superposition is pretty handy. We can also use superposition to draw shear and moment diagrams, right? If we have some complicated scenarios, we can use superposition to break those down, draw the individual shear and moment diagrams, and then re-add those back together. So let's take a look at how that goes. All right, so we've got the same beam from last time. I've added a few extra dimensions here so that we can get the math to work out. So the beam is 10 feet long, and we're going to add our 15-pound load back in. You can see our 15-pound load is 3.33 feet from our roller on the right, which would give us reactions of 10 pounds at the roller and 5 pounds at the pin. So now we can draw our shear diagram for this 15-pound load and its reactions. All right, so if we do our shear diagram, we start on the left at 0. We're going to move up by a value of 5 pounds because that's the value of our reaction. And then we've got no forces acting on the beam between our 5-pound reaction and our 15-pound load. So we go straight across. We hit that 15-pound load, and that's going to bring us down to -10, right? So 5 pounds minus the 15-pound applied load gets us to -10. So then there's no more loads between our 15-pound load and our 10-pound reaction at the roller, so nothing happens there. We go straight across, we hit the upward 10-pound reaction force, and back to 0 we go. So that's a good shear diagram for our 15-pound load. So let's look at what happens when we add the 10-pound load. All right, so that 10-pound load induced reactions of 8 pounds on the left and 2 pounds on the right. So let's draw that shear diagram. So starting at the left at 0, we're going to go up 8, and then we go straight over till we hit the 10-pound load, right? There's no change in shear between our reaction and the 10-pound load. And the 10-pound load is going to push us down to -2 pounds, right? And then that -2 is going to go straight across until we hit our reaction all the way on the right, which is +2, which brings us back to 0. All right, so right now we have graphed 2 shear diagrams, one from our blue 15-pound load and one from our orange 10-pound load. And we're going to use the principle of superposition to add these together to get our shear diagram. All right, so starting on the left, we can add our shear up right at the pin, and that would be 5 pounds plus 8 pounds, right? So that would be 13 pounds of shear at our pin, right? And that value of shear remains unchanged until we hit our 10-pound load. So now we can examine our shear boxes between our 10-pound load and our 15-pound load. The blue is bringing 5 pounds of positive shear, and the orange is bringing -2 pounds of, or 2 pounds of negative shear. So we add those up, so 5 plus -2, so now we're at 3 pounds, right? So just kind of superimpose the 5 from the blue and the -2 from the orange to get our 3 pounds of green. And now if you look at the space between our last vertical purple line and the end of our shear diagram, where blue is bringing -10 pounds of shear and orange is bringing -2 pounds of shear. We add those up, we get -12 pounds of shear. And if you recall from the previous slides that our reactions at the pin were 13 pounds up and at the roller were 12 pounds up, and then this shear diagram would correlate with those reactions that we calculated earlier. So we can also use superposition to combine moment diagrams for complicated scenarios. In this case, we're just going to stick with our pretty simple scenario. We probably could draw this moment diagram without using superposition, but we're going to do it anyways. That way you can apply this knowledge to some more difficult scenarios. So we've got everything still drawn from the previous example. So you'll have to recall back to our shear diagram for our blue 15-pound force. So to find our moment diagram, we just find the area under the curve of that blue shear diagram, right? And this is what our moment diagram ends up looking like. So we get 33.3 pound-feet of moment at a location that's 3.33 feet from our right roller. So that's our moment diagram that we figured out from our shear diagram on the previous slide. All right, and then you'll see that I've noted that we have 10 pound-feet of moment where our orange 10-pound load is at. And you'll see why we need that in just a minute. All right, so now we've got our orange moment diagram that we've also just found by calculating the area under the curve of our shear diagram from the previous slide. So our maximum moment from the orange is 16 pound-feet, and that's located at the location of our 10-pound load. As you can see, I've also noted that there is 6.67 pound-feet of moment at the location of our blue 15-pound force. So the reason I put those on there is now we can use superposition to add these two together. All right, so we'll start at the left end. So the left end, there's no moment in either diagram, so we have no net moment at the left end, and then we'll look at what our moment is at our first purple line. So from the blue, we have 10 pound-feet of internal moment, and from the orange, we have 16 pound-feet of orange moment. Right, so we're starting at 0. We're going up by value of 16 plus 10, so 26 pound-feet of moment at the green line, right? So superimposing those two is what we get. Now we look at our second purple line. We have 33.3 pound-feet of moment from our blue force, and we have 6.67 pound-feet of moment from our orange force. All right, so adding those up, we get 40 pound-feet of moment at the second purple line. And then if we look at the last point, at the far end where the roller's at, we end up back down at 0 moment for both the blue and orange diagrams. So 0 equals 0 plus 0. All right, so that's superposition of our moment diagrams. You notice that we added up the moments based on their location on the beam, right? We can't add the 33.3 pound-feet of moment to the 16 pound-feet of moment because they're not co-located on the beam, right? We have to add things based on their position on the beam, which is why I had to find the values of moments at those critical points on those purple lines. So another way we can attack moment diagrams is we can also add up the slopes of our moment diagrams. Essentially, the slope is just an equation, a linear equation, and so we can add those up. So that's sort of what we're going to have going on in this this slide here. So our blue diagram has a slope of 5 pound-feet per foot on the left, and negative 10 pound-feet per foot on the right. And those are just the magnitudes from our shear diagram. If you go look 2 slides back, the magnitude of the blue shear diagram is 5 on the left of the load and 10 on the right. So that's how we derived those slopes. If we look at our orange moment diagram slopes, we've got 8 pound-feet per foot on the left and negative 2 pound-feet per foot on the right. Again, that's just the magnitude of our shear diagram. So how do we superimpose these? Well, we can just add the slopes together based on their location. So if we start on the left, we have 8 pound-feet per foot, and then up to the purple line, So we start on the left. If we look at our blue moment diagram, we have 5 pound-feet per foot. And then if we look at our orange diagram, we have 8 pound-feet per foot, and that's between the pin and the purple line. So our slope there is going to be 13 pound-feet per foot. right, for those first 2 feet, so we can derive that the magnitude of our moment at that first purple line is going to be 26 pound-feet per foot, which is the same thing we found on the previous slide. So if we look at the space between the 2 purple lines, the blue is still bringing 5 pound-feet per foot of slope, and the orange has now changed into negative territory, so negative 2 pound-feet per foot, so we can add those up. This is going to give us 3 pound-feet per foot is our slope between the 2 purple lines. That distance is 4.67 feet. So if we multiply 4.67 feet times that 3 pound-feet per foot, we get 14 more pound-feet of moment. And we add that to 26, and that gives us a value of 40 at the second purple line, which is the same value we found on the previous slide. All right, now looking at our last block here between the second purple line and our roller on the right, we add up our 2 values of slope, negative 10 pound-feet per foot and negative 2 pound-feet per foot. It's going to give us negative 12 pound-feet per foot over a distance of 3.33 feet. So that would be a total change of 40 foot-pounds of internal moment. So we were at 40 at the purple line. Over the course of our 3.33 feet, we lost 40, so that brings us right back down to 0. So there's a couple different methods to use superposition to draw your shear and moment diagrams. All right, and the other piece to this lecture we're going to talk about today is deflection. All right, so for deflection, we're going to use the symbol delta here, which is that triangle, right? And deflection essentially is how much did our beam change shape. And the way we measure that is we look at the neutral axis of the beam before we put the load on it. Then we look at the neutral axis after we loaded the beam, and we find the distance between those two. So if you look at our picture here, we've got the neutral axis listed before the load, which is that straight line, the neutral axis after the load, which is that curved line. And then we have 2 red lines here, and those red lines depict the distance between those 2 neutral axes at the center of our beam. And in this case, that would give us our delta max, our maximum deflection, should be right there in the middle, right? So deflection is measured in length, right? So deflection is the distance between those 2 neutral axes. We typically use inches to denote deflection. Important thing to see here is that deflection changes as position along the beam changes, right? You know, if we're over at our connections at either the left or the right, the neutral axis has not moved since the load, right? So deflection at our very ends, at our boundaries, is still 0. But as we move towards the middle from either side, our deformed shaped neutral axis moves away from the original neutral axis. Right, so our value for deflection continues to increase in this scenario as we move away from our connections or our boundary conditions. All right, so deflection is not a constant number across our beam. Deflection changes with position along the beam, and there is a maximum deflection that we are typically looking for. So what dictates how much deflection we're going to get? Well, big thing is our loading scenario, right? The way we load the beam is going to really change how we're going to get deflection. Another big thing is what kind of material are we using? Are we using steel or wood, right? What's the modulus of elasticity? So the higher the modulus of elasticity, the less deflection we would probably expect to see for a beam. And then also we've learned that beam stiffness is related to geometric properties, right? So typically we just care about Ix when we're looking at beams. So our deflection is based on also our moment of inertia about the x-axis for our beam. And then the third piece is what are the boundary conditions? What kind of connections do we have on our beam? Is it fixed, pinned, rollers? That's going to change how our beam deflects. So the way typically that we find deflection is we actually do a double integral of our moment equation. All right, or we could do some modeling, but that's a little in depth for our class. And luckily for us, there is this thing called the National Design Specification, or the NDS, where someone has gone through, went through a whole bunch of different types of loading scenarios and boundary conditions, and put together formulas that help you calculate deflection for a given scenario. We end up essentially with a bunch of different charts with these plug and chug formulas that'll help you calculate deflection. The big thing is we got to make sure we pick the right chart so we get the right formulas, and then obviously be careful with units. You know, a lot of times the length of our beams is given in feet, right? But then our deflection's in inches, so we have to do some unit calculations to make sure that we get everything in the units that we want. All right, so NDS introduction. So we have a little screenshot of their front page of the NDS. Kind of walk through how we're going to use this so we are successful. So steps for our success. First thing is we want to make sure we have a nicely drawn free body diagram, right? You know, if we have a complicated scenario, we might want to break our free body diagram up into a couple, you know, different scenarios. We might want to have 2 or 3 different scenarios, nicely drawn. And then once we have our nice free body diagrams drawn, we're going to go into the NDS and we're going to pick the figures that correspond with the free body diagrams that we have drawn for our beams. As an instructor, we're going to provide you a copy of the NDS. It should be in your Google Drive somewhere, wherever your instructor has told you they put it. So NDS is a great tool. It allows you to quickly calculate reaction forces. It has those equations in there. It allows you to quickly calculate the maximum moment and maximum shear. So those formulas are all provided in there. You still will need the moment of inertia and E. You know, the NDS doesn't give you those. Those are based on your problem, so you'll need to cross-check back to see what IX is or E. You know, calculate those, or calculate IX if necessary. And then the NDS also has those deflection equations. So big note on the bottom, you know, the reason we talked about superposition was, let's say we have a complicated scenario, we want to use the NDS so we can, you know, plug and chug our formulas, and we can't find one figure that describes our whole scenario. We can break it up into 2 or 3 scenarios, and then we can pick 2 or 3 NDS figures, and then we can use superposition to add up the values of our, you know, reactions or Mmax for our more complicated scenario. So let's take a look at a snapshot of an NDS figure. So this is NDS figure 1. What this is showing is a simple beam uniformly distributed. So this beam would have a pin reaction and a roller reaction on one side or the other. In this case, it doesn't make a difference. All right, so the beam has a length L, right? And so we're just going to go through some of these values or symbols you'll typically see in the NDS. So our first equation, we have R equals V. So R is the value of our reaction force, and V is the value of shear, right? So R equals V, and then we follow the dots over, and it has an equation. It says WL squared over 2. But what the heck is W? So W is the magnitude of our nice distributed load there. So that might be, you know, 10 pounds per foot, right? So that would be W. L would be the length, and then it's all divided by 2, and that will give you the value of the reaction on either side and the value of shear on either side, which in this case is the maximum value of shear. To note, not all scenarios, the R value is going to be the same on both sides. So you'll have to check. There'll be an R1 or an R2. Just be sure to take a look that you're solving for the correct R value based on the scenario. So the second equation here, I've got a little blue box around it, so it says Vx. So what that's saying is the value of shear at any distance x from the left, right? So all these blue boxes sort of correspond with each other, right? So Vx, so if we look at our figure on the left, there's this value x that's been boxed, right? So what it's telling you is that any distance x that you decide to choose, you can use this equation to calculate the shear. Right, so that equation's there, so W times L over 2 minus X, right? And so X is any distance you choose from the left support there, and that allows you to calculate the shear at any point along the beam. We also got a great equation for M max. It tells you where it's at, so M max in this case is at the center, WL squared over 8. We've got an equation for the moment at any x distance away from the left reaction, so mx, remember that x is just an arbitrary distance that you pick. It could be 1 feet, 5 feet, 10 feet, 20 feet away from our left connection, and that will calculate mx for you just by plugging in that value of x that you choose, or maybe that's defined in the problem. Got a couple other good equations here, so we have delta max, right? So remember, delta is deflection, so maximum deflection in this case is at the center of the beam. Right, so I've got a red dot that sort of represents where the center of the beam is. That blue dot there represents, if you were to analyze something at a distance x, right? So blue is for x, and the red is the center. Right, so analyzing deflection at the center of the beam, we see that the equation is 5 times W times L to the 4th divided by 384 EI. So this is where things get a little sticky with units. Typically the length of your beam will be in feet, and I is going to be in inches, and W is going to be in pounds per foot. So you may want to just go ahead and start yourself off with success and change W to pounds per inch, a little unit conversion for that. Change your length to inches. That way everything lines up with your moment of inertia being in inches to the 4th, and typically E is in pounds per square inch. So everything is in pounds and everything's in inches to some dimension, and that will give you an accurate value for delta max. Remember, delta is how far is the neutral axis after loading as compared to where it was originally. So how much has this thing bent? And then that bottom equation there, so that's delta x at any point, right? So if you want to calculate deflection at any point, then you can use that equation there. So pretty long, complicated equation, but same thing sort of stands. Convert all your dimensions probably into inches, to make the problems just a little bit easier for you. All right, so superposition of deflection. So this is probably one of the tougher things to do, because grabbing the value of deflection, at every point is a pretty difficult task. So we have these double integral equations. They're long and complicated. We saw that on the last slide. I've also, on this slide, included the delta equations for those point loads that are on this beam, right? And so pretty long, in-depth equations. We see that there's multiple equations you have to use. So really graphing the deflection accurately along the entire length of the beam is fairly difficult, right? So we typically are not going to do that. We are just going to give you guys a critical location to calculate your deflection at. So that might be at the midpoint, or 3 feet from the left reaction, or 3 feet from the right reaction. So if you've got two different scenarios, you'll just calculate the deflection at the specified point, right? So whether it's the midpoint for both, or one side or the other for both, but you have to calculate the deflection at the same location along the bead for each of your superposition scenarios, and then you can add them up. So one thing you cannot do, you can't look at the NDS and say, okay, delta max for scenario 1 is this, delta max for scenario 2 is that. And so I can just add up these delta maxes without considering where on the beam these are located. In this case, delta max could be for one scenario is at a different location than delta max for the other scenario. And so by adding those up, you're not going to get a real value of what your actual deflection is. So you have to make sure that the locations of deflection are the same for all the scenarios that are involved. All right, so here's example 1. So go ahead and watch the example 1 video. It'll walk you through how we find deflection of this beam. And if you remember, this beam was from our bending stress example from last week. Here's a corresponding NDS chart for example 1. And then example 2, again, another video. Different scenario completely from example 1. So go ahead and watch that example video. And here are the NDS figures that correspond with example number 2. All right, here's a review for this lesson. So what is the purpose of superposition as it relates to beams? So superposition allows us to break up complicated loading scenarios into simple loading scenarios, and then it allows us to use predetermined formulas and shear diagrams from the NDS to quickly and easily solve complicated scenarios. So how is deflection measured? So deflection is measured as the vertical distance from where the beam was prior to loading to where it is after the loading, and that can be measured from neutral axis before loading to neutral axis after loading. All right, this is a big point of superposition. So if you're superimposing applied forces or moments, reaction forces or moments, if you're superimposing the shear diagram or the moment diagram or deflection values, those values must be based off their location on the beam, right? This is very important, right? So superposition only works if you're adding up things at the same location on the beam. So if you're adding deflections, those deflections have to be located at the same distance x from, whichever the diagram tells you. So you can't just add the delta maxes together unless they correspond with the same location on the beam. Same thing with moment values or shear values, right? You have to make sure that the locations for the maximum values correlate, and if they don't, you just have to calculate the values for shear or moment at those selected points on the beam. And another big piece here, when you're using the NDS, make sure that you select the correct loading scenarios, right? So check your connections. If you've got a pin and a roller, that's a simply supported connection. If you've got a fixed connection, or fixed on one end and a roller on the other end, just make sure that whatever your problem is matches the scenario that you pick out of the NDS, right? If you get close but not the right one, you'll get the wrong answer. All right, thanks for watching.